As humanity stands on the threshold of interstellar exploration, a sobering realization emerges. Our current spacecraft designs are fundamentally ill-equipped for the monumental leap towards the stars. This exploration delves into the critical shortcomings of contemporary spacecraft and discusses what may be necessary for sustainable interstellar journeys. Contemporary spacecraft face significant challenges when the concept of interstellar travel is introduced. These vessels are not built to withstand the vast and unpredictable conditions of interstellar space. A primary concern is the lack of comprehensive shielding. Spacecraft are highly vulnerable to space debris and micrometeoroids, which can cause catastrophic damage over long voyages. The energy systems on board, often reliant on solar power or finite chemical fuels, are not equipped for the energy demands of extended interstellar travel. This limitation is critical, as energy is vital for propulsion, life support, and onboard systems. Moreover, the life support systems do not adequately recycle air, water, and other essential resources, a necessity for supporting life on journeys that could span decades or longer. The recycling of vital resources is paramount, as resupply missions become impractical over vast distances. Additionally, protection against cosmic radiation is insufficient, and prolonged exposure to high levels of radiation can lead to severe health issues, including increased risk of cancer and acute radiation sickness. Another significant challenge is the psychological and physical well-being of the crew. The confined living conditions aboard spacecraft, devoid of natural environments and lacking natural gravity, can lead to muscle atrophy, bone density loss, and psychological stress. The absence of natural light cycles and the monotony of the spacecraft environment can exacerbate these issues, affecting crew morale and mental health. Addressing these vulnerabilities requires innovative solutions and reimagining of spacecraft design. Advanced shielding, sustainable energy sources capable of supporting long-duration missions, closed-loop life support systems, and measures to simulate gravity are essential areas of innovations. Moreover, creating living conditions that cater to psychological well-being, including spaces that allow for privacy, exercise, and social interaction, will be crucial. Let's dig deeper. Advanced shielding technologies. The development of advanced shielding is paramount. In the vast expanse of space, spacecraft are bombarded with cosmic radiation and high-velocity particles that can damage onboard systems and endanger crew health. Research into electromagnetic, plasma-based and magnetic shielding could offer dynamic protection, similar to Earth's magnetic field, deflecting charged particles and reducing radiation exposure. Material science plays a crucial role here, with the potential for creating multi-layered shielding that combines physical barriers with magnetic and electric fields to neutralize various threats. Once the realm of science fiction, the concept of force fields could become a reality through advancements in electromagnetic and plasma research. Such protective barriers could adaptively shield the spacecraft from various external threats, providing an additional layer of defense. Sustainable energy solutions. The limitations of current energy systems highlight the need for sustainable, high-efficiency energy sources. Nuclear fusion, with its promise of abundant clean energy, represents a breakthrough technology for future space travel, potentially providing the vast amounts of power required for long-duration missions. Similarly, advancements in solar panel technology and the exploration of alternative renewable energy sources, such as antimatter propulsion, could offer sustainable solutions for powering spacecraft systems and propulsion. Closed-loop ecosystems. Emulating Earth's biosphere, the development of closed-loop ecosystems within spacecraft is crucial. These systems would recycle water, air, and waste, and could incorporate hydroponic or aeroponic agriculture for food production. Advances in biotechnology and ecological engineering could enable the creation of miniaturized, efficient ecosystems that support life, reduce waste, and provide psychological benefits through the inclusion of green spaces. Future spacecraft designs must fundamentally evolve, mirroring Earth's self-sustaining ecosystems. This evolution demands a holistic reimagining of the spacecraft as a living environment capable of supporting human life autonomously. Artificial gravity. Prolonged exposure to microgravity has significant adverse effects on human health, including muscle atrophy and bone density loss. Innovations in artificial gravity, such as rotating habitats or centrifugal force-based systems, could mitigate these effects, providing a more Earth-like living environment. Psychological well-being. The mental health of crew members is as critical as their physical health. Designing spacecraft with larger, more livable spaces that include areas for social interaction, privacy, and recreation is essential. Virtual reality environments that simulate natural landscapes or Earth-like settings could offer an escape from the confines of the spacecraft, providing psychological relief and reducing the sense of isolation. Design paradigms. The traditional aerodynamic shapes of spacecraft, designed for planetary atmospheres, may not be optimal for interstellar travel. New designs could adopt shapes that offer uniform protection and efficient space utilization, such as spherical or toroidal structures. These designs could better accommodate the systems needed for long-term survival, including more extensive life support systems in areas dedicated to agriculture, exercise, and recreation. Earth itself is a naturally perfected spaceship, and while a departure from conventional spacecraft design could very well be a perfect design for interstellar space travel, drawing inspiration from Earth itself is a naturally perfected spaceship, and the planet has great life-sustaining systems. Earth's magnetic field and atmosphere offer a robust shield against harmful radiation, a feature our spacecraft lacks. The sun's renewable energy fuels all Earth's ecosystems, a stark contrast to the finite energy reserves of our space vessels. Moreover, Earth's closed-loop biosphere and natural gravity underscore the rudimentary life support and gravity simulators aboard today's spacecraft. It meets all the criteria we've discussed about what is needed for interstellar space travel, except for propulsion. Also, as you get away from the sun, Earth won't have a source of energy. However, the protective atmosphere and self-sustained ecosystem is something our spacecrafts could learn from. These comparisons highlight the essential features missing from current spacecraft designs. This ambitious vision requires a multidisciplinary approach, blending physics, engineering, biology, and psychology to create a new generation of spacecraft. By drawing inspiration from Earth, future spacecraft could become self-contained worlds, equipped to support human life independently as they journey through interstellar space.
That wraps up today's video. If you loved what you saw, smash that like button and don't forget to hit subscribe for more awesome content. Drop us a comment below. We'd love to hear your thoughts and get a conversation going. Catch you in the next one.